Right now, we're going to continue. I have masses done with you. I'm about to do gases. Now, I've just put my details on the screen here. If any of you want to contact me by email, you get me there. If you have my numbers there, you have that already on your notes. So feel free to, if you want something clarified, just let me know, will you? Okay, good. Now look where we are and look how we're progressing through this. I have just done masses with you. Now, can I make a suggestion to you? Don't go here until you've that dealt with. Deal with that firstly, get that sorted. I'm going to deal with gases next, and we have to be careful. I have a gas syringe here, which I'm going to use in various issues in a moment, but I just want you to see what we're at here in relation to this, okay? We have Brownian motion. We have the primary properties of a gas. There are 4 gas laws on your course. You're expected to know what standard temperature and pressure is. This is the general gas equation. I would recommend you avoid it if you can. The kinetic theory of gases is a unit in itself, which we will do separately, and ideal gases. So I'm hoping to take you as far as there now, that we will be able to work out of the gas laws, and our third unit then will finish the gases, I hope. And that's where I'm going to work with from now. Okay, can I start then by referring briefly to the idea of Brownian motion. Brown was a scientist who studied physical structures in matter. And he came to the conclusion by looking at smoke particles inside in a sealed chamber. Smoke particles were big lumps of soot floating around in the air. And he observed that they had a very random pattern, that this particle was running around in a very strange zigzag way, very unpredictable and random. And this random motion suggested that there was something going on in there in that little chamber, and he came to the conclusion that gas particles were in constant random motion. Now those 3 words are very important. Constant means they're always moving. Random means unpredictable, and motion, so they're constantly moving. So the best model you could have of any gas is any sealed chamber with these particles running around inside in a precarious and unpredictable way, colliding with themselves and colliding with the walls of the container. That's effectively what a gas is, and that's what you have to work with. And I hope that's all right, that kind of thing is that. Now, what I have here is a gas syringe. I'm going to get to it very shortly, and I'm drawing one up here to give you some sense of what that's about. It's a little chamber like that, and it has a piston, okay, a little suction pad that you can push in or out. And you'd put the gas in here, and you'd seal the front of it. You put a seal on the front of it so they can't get out. And so that would be your sample of gas then, and you could work on that. Of course, if you preferred, you could get a flask, a simple flask, and put a stopper on it. Now, that's not as good because you haven't the same flexibility. And this can be helpful, but the particles would be in there again, and that would be a sample of a gas. So I suppose really of the 3 states of matter, solid, liquid and gas, the gas is the one we have trouble with because, of course, we have to contain it to study. We can't study the gas in this room for the simple reason that there is no fixed amount there. Some of it is going out the windows, some of it going out the doors, some of it is falling to the bottom, some of it is staying on top. We don't have a way of containing it. So we have to lock it up. We have to seal it if we're to study it. A fixed mass of gas means it's a sealed chamber, and that's very important. So Brownian motion said something very, very simple. Simply said, when he observed the smoke particles running around, he assumed that these smoke particles, which you can see, were being struck by a much smaller particle called the gas particle. It might have been air in there, but the particles are so small they couldn't be seen. As a result, the smoke particles running around like that, and that's very important to have that. Now, that's exactly what I want you to be aware of, that it all came out of Brownian motion, that gas particles are in constant random motion inside the sealed container. Okay, very, very important. Now, I'm about to deal with the 4 properties of the gas, and I'm going to take off this gas syringe to deal with them. Each of them in turn. Let me just show you this for a moment. This is a gas syringe. Basically, you have a stopper here at the front of it, and by opening this piston, you suck in the gas. If I push it out, I get rid of the gas, I suction it in like that. Now, if I had more time, I could well prepare a gas and suction it into this. For example, if you reacted copper with something like nitric acid, you get nitrogen dioxide, which is a brown gas, and you could then simply just suck it in like that. I'm happy for this demonstration to stick with air. If that's okay with you, I'm simply going to take this and I'm sucking that out now, so the air is being sucked into the container. And when I have a certain amount of air in there or gas in there, I'm putting the seal on it. Okay, I'm putting that tight seal on the top of it like that, and watch now. There's a gas in there now. Can you see that? Can you see that? There's an opposition there. It doesn't allow me to push the piston back in. If I push it in, it comes out again. And that's very important. Now, the properties of gases are best understood with something like this. Okay, there's the piston, there's the gas, and there's the seal. And it's very important that you can visualize this now. We always need something concrete when we're developing an abstract concept. And that's very good for this now. I'm going to deal with them. So each of the three of them in turn I'm going to deal with. I'm going to start then with each of the properties of the gas. And here we go. The first one on my list is pressure, P. Now, pressure is technically speaking nothing other than the number of collisions that the gas particles make with the walls of its container. So there are particles in there running around, and they're bouncing off the walls and the piston on a permanent basis. And that's the pressure that's there, and we need to recognize that, okay? It's the number of collisions that they make with the wall. Very important now. The number of collisions. Now, that's a very important interpretation, right? Now, let me just give you some idea then about that. When I push this in, it comes back out. When I push it in, it comes back out. Why? Because the pressure of the gas is pushing it back out. That's very important, right? They're colliding with the walls, and obviously when you squeeze them, the pressure gets greater and pushes them back out. Okay, and that's exactly what happens. So how would you measure the pressure of a gas? And the answer is simple. When I push this in, it comes back out. Push it in, it comes back out. Why does it stop when it gets out a certain part of the way there? And the answer is simple. There's pressure on the outside as well due to the air. It's called atmospheric pressure. So when I push it in, you have atmospheric pressure plus my pressure pushing it. When I let it go, it comes back out. It stops coming out when the pressure of the gas inside is equal to the pressure of the air outside. So if I could measure the pressure of the air, I'd have the pressure of the gas. And that's exactly what we talk about here. So how would you measure the pressure of the gas? The answer is measure the pressure of the air. It's called atmospheric pressure, and you'd measure it with a barometer. Okay, a laboratory barometer would be fine. Go to the barometer on the wall and read it, and it will tell you the current atmospheric pressure. If you didn't have a barometer, you could go to the Met Office, or you could ring the Met Office. Tell them where you are. You're on top of Patrick's Hill in Cork. Could I have the current atmospheric pressure, please? And they would give you the pressure in millibars, or indeed pascals, or kilopascals, or hectopascals, whatever unit you'd be looking for. Are you clear on that? So if you knew the pressure of the atmosphere, you'd know the pressure of the gas inside in the syringe. Okay? And it's very important now that you have a sense of that, right? So because the air is pushing in and the gas is pushing out, the piston stops. The piston stops in the location that is equal to balancing pressures. So the pressure outside is the air. If you can get that, then you know the pressure of the gas inside. Very good. That's the whole premise of that, and that's what we're dealing with that. So that is the first property of a gas, and we must be careful with that. Now, the next one is volume. The volume of a gas, and everybody would think they know this, and they should, I suppose. Capital V for volume. What is volume? Volume is the amount of space that the gas occupies. Okay? It's the volume of space. Okay? The amount of space that it occupies, okay? And basically it refers, doesn't it, to the capacity of the container the gas is in. If you had a flask, then of course you could fill it with water and see what the capacity was by using a graduated cylinder. If you have a gas syringe, you can see there, I'm sure, that there's a scale on it. And on my scale at the moment, I think that's reading about 82 centimeters cubed. Now, I'm not saying you can read it from where you are, but I hope you have the idea that that's 82, right? That is the particular thing we have. You can read the scale here. When I push it in, I've told you already, it goes back out. Okay, so it is a fixed volume. And that's very good. That's what you'll be doing. You'll get it on the scale. So I need to put something else into my diagram then. This is the scale. Okay, and you have the general idea as to what you're doing, and you could read the volume on that, and that's what we'll be trying to deal with. So you'd read it right there. Okay, and that's the volume of the gas. And it's the volume of the container, and that's exactly, but you must lock up the gas. If we were talking about the gas in this room, here I go again, I'm repeating myself, you wouldn't have any fixed volume. Some of the gas would be going out the windows, out the doors, okay, etc. So we wouldn't have a fixed volume. You must have a fixed volume, and that's very important. And that's V, the volume. Number 3 is the temperature. The temperature, T, is the temperature of the gas, of course, but what does it mean for gases? It means basically, in this particular case, it has to do with how fast the gas particles are traveling. If you raise the temperature of a gas, the particles start traveling faster. If you cool it down, they start traveling slower. That's a fact. And we have to relate to that, of course, in trying to deal with that. Okay, this is the speed, or the velocity, if you'd like to use that, the speed of gas particles. Okay, speed of the gas particles. So, you need to recognize then that if I was to immerse this particular thing here, this syringe, into boiling water, that the particles would speed up. And what would that be likely to do? It would be likely to affect the number of collisions. And therefore, there'd be more pressure, and I suspect the piston would move out a bit, it would expand. You probably know, do you, that you would be told with an aerosol can that you should not incinerate it. You should not put it in the fire or near heat, because the particles there would start traveling faster, the pressure would get greater, and it would cause the can to explode. So consequently, you have to recognize that that particular interpretation of temperature is very important, the speed of the particles. And how would you measure the temperature? We all know that, a thermometer, yeah? So at the moment, what is the temperature of that gas? The answer is the temperature of the room. Okay, your average room is about 18 to 20 degrees Celsius. But you'd have to measure with a thermometer. You'd have a thermometer in the room, so you'd know that. Okay, you'd know that. So a thermometer would be used here, and you all know that. Now, will you remember if they said that the container was in boiling water? Will you remember then, please, that your temperature would be very close to 100 degrees. They may tell you that, but you'll be working on that premise, and that's what it would be about. So these are 3 very important properties of gases, and you must be careful with them. I've one last one I need to add. It's small n, not capital N, now small n. It is the number of moles. Okay, number of moles, small n. And you need to be careful now with that number of moles. And I'm appealing to you now to recognize that I haven't the mole done with you yet, okay? But it refers to how many particles are actually in there. Now, there's a slight flaw in that until I get to the mole. That'll be another unit. By the way, that's my destination. That's where I'm trying to get to. I'm trying to get to the mole. You couldn't possibly do the mole without having a clear understanding of masses and gases. So just stay with me, and this will be right in due course for you. Number of moles there is n, right? So I'm showing you them now so you have a sense of what you have here. And there you go. Number of moles is the number of particles. Gas particles, I had better state. Gas particles. Now please, there's a slight flaw in that. I'd have to qualify that later, but it's fine for the moment, and it gives us a sense of what we're trying to do there with that, okay? Now, they are the 4 properties. You're doing very well with that. And I'm moving from that now, because what we must do next now is they are basically what we need to deal with now. I have the 4 properties covered for the last time. Pressure refers to the number of collisions that the particles have with the walls of the container. Volume refers to the amount of space the gas takes up. It's the volume of the container, right? Temperature refers to how hot or how cold it is, but we need to be careful of that language. We're really talking about the speed at which they're moving. At a higher temperature, they're moving faster. At a lower temperature, they're moving slower. You'd expect that, okay? And that's fine, that you have to be aware of that. And of course, number of moles is how many particles are in there. And that's very important. Now, they're all linked to each other. There's a relationship between them, and that's where we're going next, okay, to deal with them. Now, think about this now for a moment. We're about to deal with the gas laws. There are 4 gas laws on your syllabus. Before we get into them now, you're expected to treat all of them equally. The idea that one is more important than the other would be silly, because you'll end up in a situation where the one you have neglected is the one that turns up on the paper. So they must get equal attention, and I'm going to work my way through them with you now, okay? There are 4 gas laws. The first gas law is Boyle's law, and everybody should be fine with that. There shouldn't be any issues at all. Boyle's law. Now, can I make a statement here, please, again, that I want you all to adhere to? It's common for people to learn the laws. You're told to go away and learn them. Please don't learn the gas laws. There's an idea or a concept behind every law, and you must appreciate that. You're articulating an idea. You're not reproducing words, I hope, and that's very important. That's Boyle's law. Boyle was an Irish scientist, okay, Robert Boyle. Hasn't been around for a while, 1600s, okay, but you're expected to know. Boyle studied gases whose temperatures were constant. I'd expect you to know that. The minute I mention Boyle, oh, that's a gas at constant temperature. Very, very important, right? Now, we need to recognize what's going to happen here. Each of these particular properties of a gas affect each other. And we're trying to study how any one of these affects another. And this becomes very important now in what I'm going to do with you, and I hope you'll be all right with it, okay? The law says, I'm only stating it for a start, I'll come back and I'll develop the idea for you then. At constant temperature, in other words, the temperature is not going to change for a fixed mass of gas. The volume is inversely proportional to the pressure. Now, here we go with this. I must be very careful with you because we're dealing with it all the time. I'm going to delete this piece again now, but I need you to recognize what I'm at here now. Very, very important that you know what I'm doing. We have 4 variables. Watch them, please. P, V, T, and N. Boyle said that at constant temperature for a fixed mass of gas, in other words, if you keep the temperature constant and the number of gas particles constant, you can then study the effect of pressure on volume. And that's very important, that the volume is inversely proportional. We have a formula for that. The volume is inversely proportional to the pressure, okay? That V is proportional to 1 over P. Now, that's a very obvious statement. You knew it already, but 'tis articulating it as a scientific concept is what's demanding about this, and you must be careful. Now attend to it please for a moment, just make sure you know what you're doing. There are 4 variables. If you want to study the effect of any one variable on a second variable, all the others must be kept constant. Now think about that for a minute, okay? If you were trying to do some kind of analysis of the cause of something, you'd have to eliminate all other causes to link the particular suspected cause to what you're dealing with. Okay, and that's very important that you have that idea. I could put something to you like this now. If we wanted to work out what the effect on the wearing of a carpet was on shoes on the carpet, how shoes were wearing a carpet, we'd have to make sure that only people wearing shoes were on the carpet. Okay, we couldn't have anybody else in here other than that, meaning you couldn't be there in your socks, you couldn't have anything else, that you have eliminated everything except shoes and carpet. And over a period of time, you'd say, look at the effect that the shoes have had on the carpet. Okay, and that's a very important idea in science now. If you ever want to study the effect of any one variable on another, it's crucial that the other variables are kept constant. And let me just illustrate that for you now with my gas syringe again. It's very easy. We are saying here something patently obvious, that the volume is inversely proportional to the pressure. In other words, if the pressure gets bigger, the volume gets smaller. Or if the pressure gets smaller, the volume gets bigger. And just watch for a moment, please. If I push on the piston, I'll pressurize the gas. I will increase the pressure. And what do I do in the process? I reduce the volume. If I leave it go, it goes back out. If the pressure gets less, the volume gets more. As it happens, if I pull out the piston, if I pull it outwards, I reduce the pressure. The lads inside there have more room to run around, less collisions, less pressure, and therefore it goes back in again when I let it go. So if I reduce the pressure, I increase the volume. If I reduce the pressure, I increase the volume. If I increase the pressure, I reduce the volume. Patently obvious. If you compress a gas, increase the pressure, you'll reduce the volume. And that's exactly what Boyle said, provided the temperature and the amount of gas is constant. That's why I need a stopper on that, so the lads can't get out. The particles are fixed. At constant temperature, for a fixed mass of gas, the pressure is inversely proportional to the volume. As the pressure gets bigger, the volume gets smaller. Pressure gets bigger, volume gets smaller. I hope that's okay. That's an idea now. And I'm appealing to you again now, please. Stop learning that as words. That's a concept. You must think about the concept and you'll have it right every time. Very good. The attachment to that, you really don't need to know a lot on it. Will you accept for a moment, please, that these are graphs which illustrate this particular thing. This graph is saying, look, as the volume gets bigger, the pressure comes down. That's what we said. Or if you prefer, that's a more meaningful graph. The pressure, and not the volume, but 1 over the volume, are related to each other like that. Okay, be careful. Pressure 1 over V. In other words, there's an inverse of the volume for the pressure. You won't be asked to plot any of those graphs. You will not be asked that. Don't worry about it. You won't be asked it, okay? But what you would be asked, of course, is this here. That's the only formula you need. V is proportional to 1 over P, is what Boyle had said. Whenever you have a proportionality sign, you have equals a constant in there. K is the proportionality constant, and therefore solve for K in that. K is equal to PV. PV is a constant for every gas, meaning if the pressure gets bigger, the volume gets smaller, so the product would always be the same. If that got smaller, this gets bigger, so the product is always the same. Have you got that idea? That's exactly what you want. So PV is a constant for a gas at constant temperature. PV is a constant. And so we use Boyle's formula here. That's Boyle's formula. P1 V1 equals P2 V2. That's the formula for Boyle. Because, of course, what's it dealing with? That's dealing with a gas at constant temperature. There's no temperature involved. And that's exactly what you want. When would you use that formula? It's simple. If I gave you the volume of a gas at 1 pressure, and I asked you to calculate it at a different pressure, that's the formula you'd use. Watch, please. I'm looking at this. This is 82 centimeters cubed, this gas. All right? And the pressure in this room at the moment is 100 kilopascals. I'm just telling you that now so you know it, okay? I've gone to a barometer and that's 100 kilopascals, right? So I have a volume of 82 and it is 100 kilopascals. I could now ask you, what volume would this gas have if the pressure decreased by 10 kilopascals? That's it. You take that formula, you're given the volume at a known pressure, you'll be given a new pressure, and you'll calculate the volume at the new pressure. No mention of temperature. The temperature is constant. At constant temperature, for a fixed mass of gas, the pressure is inversely proportional to the volume. I expect you to be able to reproduce that as a logical statement. And the only other thing you need is that formula. That's Boyle's formula. That's Boyle's law. It always refers to gases at constant temperature. If there is any question of the temperature changing, it is not Boyle. You can't use it. It's as simple as that. That's law number 1. And I'm going to law number 2 now, which is Charles's law. Charles's law, Charles is a French chemist, and he developed the relationship between various properties of gases at constant pressure. Boyle was studying gases at constant temperature. Charles was studying gases at constant pressure. Okay, and it's very important you realize then what's happening. And the statement is as follows. At constant pressure, because that's what he's dealing with, for a fixed mass of gas, the volume is directly proportional to the temperature. And on the Kelvin scale, it's just a technicality. So watch me, please, what I'm going to do here with this. Here are the 4 variables again, P, V, T, and N. Right? And it says here clearly on this, right, at constant pressure for a fixed mass of gas. These 2 are constant, so we can now study the effect of volume and temperature on each other. Saying that very quickly again, at constant pressure for a fixed mass of gas. The pressure is constant and the number of particles. Fixed mass of gas, number of particles is constant. That's constant, that's constant. So we're studying the effect of temperature on the volume. And sure, that's patently obvious as well if you're willing to think about it. What do you think would happen, this gas, if I put it into boiling water? And the answer would be, of course, that you'd raise the temperature, the particles would travel in faster, that would create more pressure, so it would push the piston out to reduce the pressure to keep it constant. So effectively what would happen is, the pressure stays constant, you've raised the temperature, so you'd raise the volume as well. Gases expand when they're heated. I don't think you need me to tell you that. Most materials expand when they're heated, and gases are no different. So at constant pressure for a fixed mass of gas, the volume is directly proportional to the temperature. Okay, temperature is measured on the metric scale. Don't worry about that now. That's fine, but that's what you want. Now that's nice and straightforward. We need to be aware of that. And there's an appropriate formula to go with that, so attend to it now, please. The graph there shows you exactly what happens. As you raise the temperature from 0 degrees to 100 degrees, the volume goes up. Notice it doesn't go through zero. If it went through zero, you'd be saying the volume was zero. If the volume was zero, there'd be no gas there. So obviously, even in ice, the gas still has a particular temperature, okay? This is room temperature here. Look, its volume would be somewhere there. So as you move up like that with the temperature, then the volume goes up as well. That's exactly what's involved. V is proportional to T. V equals a constant times T, and therefore V over T is a constant. And therefore, we get a law, again, we get a formula for Charles's law for calculation purposes. There is the formula for Boyle, and here's the formula for Charles. V1 over T1 equals V2 over T2. And that's Charles's law. Okay, very easy, no problem with that at all. Okay, it's simply suggesting to you that the volume depends on the temperature. Now, that came out of that, and that's what I need you to know. Now, can I clarify again, please? You're expected to reproduce that statement as a logical idea. Stop learning the words, please, and think about what you're saying. If the pressure is constant for a fixed mass of gas, then if you raise its temperature, you'll make the volume bigger. That's all there is to it, and that's exactly, and there's the formula I want you to know. V1 over T1 equals V2 over T2. I'll give you a tip in a moment as to how to remember them without having to go through a lot of bother, but that's it. Now, when would you use that formula, or how would you use it, is the question I'm dealing with now. Are you attending to this now, please? If I told you, I'm back to my circumstances again here now with my syringe. If I was to say to you, the volume of the gas in here is 82 centimeters cubed, and the temperature of this room is 20 degrees Celsius. I could now ask you, what volume would that gas have if I put it into boiling water? You have the volume in this room, you want the volume in boiling water. How would you do that? Easy, right? You're given the volume in the room, you're looking for the volume at 100 degrees. So you have that, and you find that. Now please, I have an attitude to formula, chemical formula and general formula, that they all have a function, they have a use. You need to see them as a kind of an implement or a tool, and you'd use them to basically come out with a solution. You don't need to have all the background to this at this stage. You just need, that's a functional formula. Oh yes, I'd use that formula if they gave me the volume at one temperature, but I needed it at another temperature. Very good, that's exactly what it is. And the one above, oh, if I got the volume of a gas at a certain pressure, I could find the volume at a different pressure. And that's exactly what you want there, nothing more, nothing less than that. So that's the first two gas laws. I hope they're okay with you. I'm going to finish this module now by introducing you to the general gas equation. And you don't need anything other than the formula for it. The general gas equation is a combination of Boyle and Charles. And I'll be recommending shortly that you don't do calculations with it if you can avoid it. There's a better formula coming up in a subsequent class, and we'll deal with that in due course, okay? But look at this for a moment now, please. According to Boyle, PV is a constant. And according to Charles, V over T is a constant. Are we okay with that? If you put the two of them together, you get PV over T as a constant value. Now it is. For every gas, the volume is that particular quantity, PV over T, is constant for every gas. Now let me tell you about that. This is a certain volume of a gas. I'm talking about it all the time now, but this is 82 centimeters cubed. That number 82 means absolutely nothing if you don't know the temperature of this room right now and the pressure in this room right now, which is atmospheric pressure. So you'd be getting a barometer to get the pressure in the room, and you'd be getting a thermometer to get the temperature in the room. So you would know this volume at this pressure and this temperature in this room. Now, if you didn't know the temperature and the pressure, then that volume is useless. And let me develop that a little further for you now. If you were to come back here tomorrow's to be a colder day, I would suspect you'd have a different volume for that gas if I just left it overnight. Because the volume is dependent on both the temperature and the pressure. So quoting the volume of a gas is a waste of time if you don't know the temperature and the pressure. So that quantity is very important for all gases. A volume is meaningful if you know the pressure and the temperature at which it exists. Very good. And that's what we want, and that's what we're dealing with. There should be no issue with that. Now, stay with me while I bring this to a conclusion. Now, we get the general gas equation then by saying, because that's a constant, PV over T equals PV over T. And we call them ones, and we call them twos. Now, this is a functional formula. It's not difficult in any way now. It's a combination of Boyle's and Charles, as you can see. Boyle is PV, and Charlie is V over T. So put the two of them together, you get PV over T. It's a constant for every gas. When would you use that formula? Now, I've asked you the question already. We have three formulas on the board here. When would you use them? I would use that if they gave me a volume of a gas at a stated pressure, and they wanted the volume at a different pressure. No mention of temperature, or they would tell you the temperature was constant. Very good. That one. When would I use that? If I was given the volume of a gas at one temperature, but they wanted the volume at a different pressure, at a different temperature, excuse me, you could then use that formula, okay? Given the volume at one temperature, find the volume at a different temperature. No mention of pressure, or they would say the pressure was constant. That'd be giveaway, by the way, to Charles. And this is the general gas equation then. If they gave you the volume of a gas at a stated pressure and a stated temperature, they gave you a volume at a stated pressure and a temperature, you could get the volume at a different pressure or a different temperature. And that's very important. So simply, you'd put your units in there for that, and that, and you could get the new pressure. They gave you the pressure at one volume, they gave you the volume at one temperature and pressure, you could find the volume at a different one. Now, can I just go back on that again? I want to be sure everybody's clear. It's only a functional formula. I'll be asking you to avoid it. P1 V1 over T1 equals P2 V2 over T2. If I give you the volume of a gas at a stated pressure and a stated temperature, you can find the volume at a different pressure and a different temperature. Okay, and so let me put that into numbers for you then. Here we go. The volume of this gas is 82 centimeters cubed. The temperature of this room is 20 degrees Celsius, and the pressure is 100 kilopascals. You put the volume in there, the pressure in there, the temperature in there. Now, I could ask you the question, what is the volume of this gas if the temperature went up to 24 and the pressure came down to 99? So you'd be given a new pressure and a new temperature, and you'd be looking for the new volume. The volume will change if the pressure or the temperature changes, and that's very, very important that you can deal with that like that. Now, that's a suitable place to break this unit. There are two very important laws. You've only two formula. And of course, as well as that, you have the general gas equation. I have issues with the general gas equation that you have to be careful with it because it leads to a lot of calculation and there are easier ways of working it, but we'll deal with that later. I am saying, however, units do not matter here. Units do not matter. If that's centimeters cubed, that must be centimeters cubed. If that's pascals, that must be pascals. If that's degrees Celsius, that must be degrees Celsius. But other than that, they must be the same. Other than that, you can use them, and there would be no issue with that. Now, I'm bringing this unit to a halt. I'll be then moving into the next one where we develop this further, all right?